Hey folks, I'm Jen Foxbot and welcome to Maker Quest. In this episode, I'm going to talk about magnets, which are one of my favorite subjects. So we've covered electromagnets, but what about pure magnets? Well, they're a miracle, right? No, just kidding. They're actually a pretty well understood natural phenomenon, and it's definitely more science than magic, although I kind of like to think of science as like real world magic, and sometimes it is, especially when you're talking about forces that are totally invisible to us, like magnetic fields and electric fields. Magnetic fields are typically defined in two main ways. The first would be the direction, so that's the orientation of the magnetic field lines. And then the second characteristic of magnetic fields is the magnitude or strength of the magnetic field. So like the pushing, pulling force that they have. Whoop. So these are very, very strong. And ow! Yeah, be careful with your fingers. What about the magnetic field lines? How do we figure out direction? Well, that's actually where a compass comes in. And so basically what a compass tells us is the orientation of whatever pole that we're looking at. So for example, with a compass, when it orients itself, its north pole is pointing towards the Earth's north pole, or we call it the North Pole. And so if you have a compass and you have it underneath or next to a permanent magnet, you can kind of move around the permanent magnet and see how the compass needle changes. So you can actually create a really simple version of a compass at home with just a cup of water, an object that floats. So I just cut the bottom off of another cup, and then a magnetic material like a nail would work. So I put that on the floaty bit, and then I can take a magnet and kind of make it dance around. Woo! Alright, so that's a compass. What about materials? What's different between this magnet and this nail, or even the one that I used for the compass? Well, this is a permanent magnet. And basically, as you might expect, that's a magnet that has an intrinsic magnetic field, or basically a magnetic field that's, well, permanent. So you can use these to magnetize other things. And then you also have ferromagnetic materials like iron, cobalt, nickel, that type of thing. They're the materials that respond the most to permanent magnets. So they're pretty easy to find around the house because you can just take a fridge magnet and see what sticks to it. So, I guess not so much. It's kind of a weak magnet. Anyway, so then, okay, so we have permanent magnets, ferromagnets. We also have paramagnets. And paramagnetic materials respond very weakly to an external magnetic field. So, to really figure out what's going on, we need to go to the atomic level. And what is happening at the atomic level is that for example, in this nail, you have billions and billions of atoms that are making up just this tiny little nail. And around, within each atom, you have electrons orbiting around the nucleus. And so because the electrons are moving, they're charged, and as you might remember, a moving electric field generates a magnetic field. So each atom actually has an associated magnetic field with it, with a north and south pole. And in a ferromagnetic material, these tend to form clusters of atoms, and so you get these little clusters of, like, I don't know, a few hundred atoms or something like that, each in the same orientation. And then within the entire material, all of these little clusters are oriented in different directions. They're completely random orientations. So when you take the material as a whole, they basically cancel each other out. So in effect, you get a material that's non-magnetic, based on what you and I can see. But ferromagnetic materials can be magnetized in the presence of a magnetic field, and that means that if you take a magnetic field and you connect it to, or put it in the presence of a ferromagnetic material, you can cause the atoms in that material to orient in all the same direction. And for ferromagnets, that orientation will stay even if you take away the magnetic field. In paramagnets, they will just go back to the random orientation, not be magnetized, etc. So ferromagnets are super cool because you can take a regular nail from at home and magnetize it. So to show you an example, I have these scissors which are not magnetized, and trying to pick up the nail, nothing happening. So, well, pretend that didn't happen. So if I touch it to a magnet, I'll magnetize it, and then I can pick up the nail. Yeah! So almost like magic. I will leave you with kind of a tricky question, and that is, why do we call the North Pole of a magnet the North Pole? And how does that give us information about the Earth's North Pole? The Earth's physical North Pole up in the Arctic? Let me know if you have any clarification on that. It's kind of a tricky question. To answer last video's question, I asked, why do we need the protective casing around the sound detector? And that's a fairly simple question, actually, if you watch the sound video that I posted before that. And it's because we need to essentially eliminate physical vibrations triggering the sound detector, so that the styrofoam case effectively insulates it from tiny little micro vibrations caused when I walk around, or if I accidentally bump into it or something like that. So, pretty simple. Alright, so please let me know if you have any questions about that explanation or about magnets, because they're awesome. Thank you for watching, and please subscribe.